So 7 years ago, I had no intentions of being an educator. But my wife was pregnant. I decided to see what the school system in Canada had to offer for my upcoming child. I walked in. I walked in to
mad at me because I always by making too much noise. I'm sorry. Thank you.
I walked into a math fair in Calgary, and I was blown away by the intensity of the students. After 20 minutes, I sat down in front of one grade 2 child, and she presented me with this problem here. There are 3 frogs on the left, 3 frogs on the right. The frogs on the left can only move to the right. The frogs on the left can only move right. And frogs can jump 1 space over another frog, or can move 1 space into an empty lily pad. So this was her problem. And the more that I struggled with this, the more her evil little grin got bigger, and she knew that I was a token mathematician, and I was totally humiliated in front of this grade 2 student with this big smile. And I left that experience and I just thought, this is the most marvelous gift that you can give to a child. So I walked out of that, and I quickly got adopted as a resident mathematician in a school in Calgary. And I left that position and I started up Math Pickle. The only purpose of Math Pickle is to help teachers with their #1 problem. And that is how to address the spectrum of student ability in their classrooms. What I'm going to be talking about today is a new talk. I just decided to talk about removing the stigma of failure from the classroom. If you go to the website, Math Pickle, it's a video-based it's got video-based resources. So you can scroll down, you can go to the grade 3 section and scroll down. And I'm going to pick this just for a sample, this grade 3 $1 million problem. And we're going to play that.
There's an unsolved problem of mathematics from 1967 that is made up of a whole bunch of smaller problems. And these prove to be the best way to engage students in subtraction. In this video, we're going to learn how to solve one of these problems. We're going to see some children solving them, and we're going to learn how to make them ourselves.
Those 2 boys were working on this problem. How do you solve it? You start by placing the odd consecutive integers starting with 1 on these blue circles. Then you ask yourself, what is the difference between those connected circles? So 5 and 1 are connected here, so we have to put 5 minus 1 on the red line. So we're going to do that. 9 minus 1, those are connected, so we're going to put 8 on that line. At the bottom we have 13 and 11 connected, so we have to put 13 minus 11, that's 2 on that line. See how it works. So we have to do that for all of the lines, and we win whenever all of those are different. So you see we've won here. Oh, we haven't, because there's a problem. We have these 2's. We have 2 2's. So that's not acceptable. All those red numbers that we had have to be different in order for us to beat this dragonfly. How to solve the problem? Well, not easy to see, but well, one way to do it is to swap those two, and then we have 11 minus 1, that's 10. We have 13 minus 7, that's 6. And now all of the numbers there are unique. We have beaten the dragonfly. The first problem that I give to students is not as hard as a dragonfly. This is a really hard problem. Instead, I would give something with less blue circles. So maybe this wasp or this butterfly. But my favorite one is probably this starfish. And it's my favorite because if you put the number 1 or the number 11 in the center, then you solve it, guaranteed. Now let's see it done incorrectly. Now let's eavesdrop on some students working on a problem that's a little bit tougher.
Watch the emotional engagement.
Okay, one, remember one in the middle. One. I do. One, and then just do random numbers. Remember random numbers. Another 5. No. 15. Wait, no, let's put 5 right here. 15. Yeah, 7. And then I'm gonna 13 right there. How about 11? Yeah. 10, 12. I think 12.
A big motivator for some students in solving these problems is the joy of getting a new animal and a new puzzle to solve. And I love playing with this, so I might ask, do you want a really vicious animal? And then I give them a bunny rabbit or a dimetrodon. I think using beautiful images is very important. There's a lot of students that are very much empowered whenever they see and are playing with beauty. Here's a photograph of a hermit crab by Vanessa Pike Russell. It's a work of art by itself. Here we have 7 blue circles. This is a tough problem for grade 3s. You do not want to go far beyond 7 blue circles whenever you're constructing a problem. And there is room for you to construct problems, especially whenever you give the students the openness to design their own monsters or their own sharks. So you get them to draw their images, but you retain control over how many blue circles they get. That way you maintain control of how hard a problem you're giving to the students. So here we have 6 blue circles in this shark, and that's a moderately tough problem. 7 would be very tough, and 8, I think, you might not ever go to 8. Okay, let's look at some of the rules that you need for drawing your red lines. So you've got your blue circles. What are these sufficient red lines? No, everything has to be connected. So yes, this is a possible problem that you could give to your grade 3 students. Is this one acceptable? No, it's not, because there is a loop, and you can have no loops in your designs. Is this acceptable? No, because it's not connected. The top isn't connected to the bottom. Let's connect them. Is this acceptable? Yes, everything's connected, and there's no loops. So this is another problem that you could give to your grade 3 students. Again, we use consecutive odd integers starting with 1. Who do we have to thank for such a beautiful bunch of problems? Georg Ringo was one of the mathematicians involved. Not only was he a mathematician, but he was also a great butterfly collector. And whenever he retired from the University of California, Santa Cruz, he donated 5,000 specimens to the university. The name for this unsolved problem in mathematics circles is the graceful tree conjecture. And basically it is, no matter how many blue circles your insectoid or animal is made up of, is it always possible to find a solution. Despite it being unsolved, this problem deserves to be in every grade 3 classroom learning subtraction.
So how do you introduce a problem like that? The way that I introduce it is by giving a failure right away to the whole class. And the way that I do that is I don't explain the rules to the question before I begin. I don't say, oh, you have to put the odd numbers there. No, I just go like this, and oh, let's choose a simpler one. Okay, here we go. So, yes, what number would you like to put in this spot here? 1, 3, 5, 7, or 9?
7.
7, okay. What number would you like to put in this spot here? 1. What number would you like to put 1, 3, 5, no, 3, 5, 7, 3, 5, or 9? What number would you like to put here?
3.
3. And what number would you like to put in this spot?
5.
Okay, now you've got a very tough choice. I'm going to guess 9. Okay, and we've won. Okay, because all of the differences are different. No, they're not. What I just did is I put myself in the failure position as well. Okay, because no, not all of the numbers are different. Where's the duplicate? 3 and 5. 5 minus 3 is 2. 3 minus 1 is 2. Okay, so the whole class has failed. I failed as well. That's removing the stigma of failure right there. Okay, let's look at another example. This is from the grade 1 classroom. And I'm not going to go through this whole video.
And it rained, and the grass got greener and greener and greener. Willy Wiggle Wiggle Worm just had to go out and splash and slither about. But when he did, a mathematician spotted him and asked, "Poor Willy Wiggle Wiggle Worm, don't you have a home? Don't you have a house? Don't you have a roof to put over your head? Let me fetch you a carton. You can live in here." And so he put Willy Wiggle Wiggle Worm inside a carton. And then he said, "Willy Wiggle Wiggle Worm, wouldn't you like to learn how to count?" And Willy Wiggle Wiggle Worm, before he could answer, got numbers written all over him by the kind mathematician. Willy Wiggle Wiggle Worm didn't know what to think. But the kind mathematician said, "I can entertain you. I will give you fun puzzles to do every day. For example, you'll arrive home one day and you'll have the numbers 1 and 25. You have to put yourself on top of them. So you see, you've got the 1 and you've got the 25, and you've managed to curl yourself around so the rest of you fits in. You see how it works?" "That's right. Do you have any requests, Willy Wiggle Wiggle Worm? What kind of things do you not want me to do in my puzzle?" And Willy Wiggle Wiggle Worm thought for a second, and he said, "I can go up, and I can go right and down and left, but I don't do diagonals." "Okay," the mathematician said, "no problem. I won't make you do diagonals. But why?" "Why?" said Willy Wiggle Worm, "because I don't want to end up like this." "Okay," said the mathematician.
That was my old way to explain this problem. So I actually would play this video in front of grade 1 students, and I'm explaining to them, oh, you can't go diagonally because of that. That's not the way I do it now. The way I do it now is, again, I give a failure immediately. Rather than explain the rules, I immediately give a failure. And the failure, we can go around a table like we did before, but you get the idea. Before I tell the rules, I'm going to just say, okay, where do you want to lay out? So we're going to put the 2 maybe to the right, and the 3 underneath, and then the 4 to the right again. And the 5, do you want to go up? Yes, thank you, sir. And you end up, oh, oh, darn it. Now I'm going to have to cut the worm in 2, and we're going to have to keep on going. Immediately, whenever you say that, the half of your class with too much testosterone, their eyes go, whoop. Okay? So implied violence is a great way to engage that half of the class. And the girls get, oh, the poor little worm, we have to save it. So you hit the emotions, you hit the implied violence, and it's a highly effective way to give a failure and then employ the whole class. This is another grade 1 problem. So this is pattern recognition. This is a book of mine that I'm trying out, and instead of making patterns easy for kids to recognize, I choose them really tough. So here we have collect beetles from the Staphylinidae family, but there are 2 imposters that you can't collect. So where are those 2 imposters? Can you figure it out? Well, this is hard. First of all, you immediately get a failure. What's the failure from a grade 1 perspective? Well, look at the word, Staphylinidae. I mean, the parents aren't going to be able to explain that, right? So this is another failure, but it's a failure with beauty behind it. It will be engaging for the kids, and this is a puzzle that I've tried out with 2 grade 1 classes so far, and it's worked out fine. I've got a book. So this one's in its exploratory phase. Can you figure out the 2? We'll label these rows, row A, B, and C, and 1, 2, 3, 4, 5. Which are the imposters? C2 is correct. You've got 1 imposter.
B5?
And B5 is not another one. So you failed. In this book, I actually point out that I failed on 2 of them. I wrote the whole book, I went back, I tried the puzzles, and I missed 2 of them. So I have in there, author failed on this problem. So that's good. This one I was successful on. I got this one, and I think I got this one. Those are the 2 there that are imposters.
Why?
Why? Yeah. Why? This is biological classifications. You can't ask why. It's just the fact that if you genetically analyze these, those 2 belong to that family. Okay, so you're going to fail, right? This is not something that you can guarantee success with. You are going to fail if you go through this book. It's a grade 1 book.
No, wait, there is a difference. Like this one on the left has these horizontal scales on its tail.
Sure, you can look at them and you'll be able to identify, oh, that's a feature, and it's a discussion point. Okay? Okay, here's a failure for the grade 4 classroom. You are now my grade 4 students. Okay, I've been employed to measure the height of this dragon worm. It's very, very dangerous, and can I have estimates, please, of the height? That is 1 meter. Oh, for Americans, that's 1 yard. Yes? Can I have an estimate based on that being 1 yard tall? Estimates, please. 3 yards tall. I'm measuring from here, not from the tail to the tip of the nose, but from the standing height from here up to here. Okay, so 3 yards. 6 yards. 5 yards. Okay, let's put in, let's see. So that might be more helpful. Okay, can I have estimates again? 6.5. Okay, now I'm looking for precision because now we've got the rules. So I want you to give a precise answer now. 6.3. 6.4. Okay, let's. And what I'm looking at is for if you can be absolutely precise now. 6.34. Okay, you're still not. I'm asking for precision here.
6.35.
6.35.
6.36.
Did I not make myself clear? I am looking for. Let's get rid of round-off error. I want precision here, people.
1 dragon height.
Okay, let's get more active. Okay. 6.3. I'm really disappointed. What I am looking for is no round-off error, people. So, okay, let's get a little bit closer. And what I'm looking for is no round-off error. If you can be precise, that is what I am looking for. Precision. Grade 4. You are a grade 4 student now. Yes, answer my question. I want precision. Okay? Well, in Canada, this would be curricular. In Calgary.
This is curricular in Indiana, or in the United States as well.
Okay.
They're supposed to learn about this.
Okay. So round off error, grade 4, grade 5. You could choose. Now you're grade whatever students for which this is curricular. So you can see the way I'm saying, okay, let's get precise, not this approximate. I want precision. People think you're hiding behind there, but I see you, John. Yes. So after many, many years, and this is the dedication that it takes, I finally managed to come up with an answer. And I'm still working on it. I expect to do this for many more years. So that's it. And then after that, I probably have another animal to do.
The height changes in time.
Yes, we can get into discussions about breathing and stuff like that. Yes, but the point is that you give a failure with impact because you add the emotion there. So I like that one. That's fun. This is a grade 2 failure. So now you're at my grade 2 class. You notice the icicles outside. Now, not all icicles are the same. So these icicles, if you look really closely, you can see some circles on them. Those circles are filled with numbers. Yeah, look at that. So, and this is skip counting. So here we have to skip count. Can everyone do this together? We have to skip count by 1, starting at 5. Okay, everyone, 5. What do you think is going to be next? 6, 7, 8, 9. Good. Okay, so skip count. Okay, let's try over here. Oh, skip counting by 2 on this icicle. Okay, everyone? 6, 8,
10, 12, 14.
And by odd numbers now, 3s. Oh, okay, 3, 5. So you see these ones. Okay. And by 5s. This is pretty tough for some grade 2 students. So let's. Okay. Did you have an idea? 15, 20? Yeah. 30. 35. Now, sometimes these icicles fall on the ground, and yeah, can you? So I got 7. Yeah, go.
What am I supposed to do?
Some students are slower, and that's okay. Yeah. So can anyone help? So skip counting by 1, 7, 6.
It might be 8.
8. Then does everyone agree?
Yes.
Everyone agree? Okay. And then you go, oh, too bad, I got you all because this icicle was lying upside down, and unfortunately you don't know whenever it's on the ground which direction it's lying. Oh, that's too bad. You all got it wrong. Failure. So you see the way this works. So then you can add interesting icicle patterns and play around. But initially, give a failure to everyone. Okay. Failure by different names. So instead of giving a red X, or instead of saying, you failed, which I sometimes do, here's a puzzle that I like. It's the grade 2 $1 million unsolved problem. And this is the way I describe it. So we have 2 bubbling cauldrons. Left, for me, okay, maybe I'll turn like this. Left and right. And I'm going to drop a frog number 1 into which pot? The left, let's say the orange or the blue one. Where do we want to drop the first frog? Into the orange or blue pot? Orange. Okay. Frog number 2, orange or blue pot?
Blue.
Frog number 3, orange or blue pot? Matt?
Orange.
Orange. Frog number 4, Trevor?
Orange.
Orange. 1 plus 3 is equal to 4. Trevor, you've been gooped. Okay? Now, in that context, everyone understands what goop means Trevor understands perfectly well, as a grade 2 student, Trevor understands perfectly well what being gooped has just done to him. And it's not pleasant. So here's failure by a different fun name. And so that's a puzzle. Here the objective is to get all 8 frogs into these 2 pots so that you don't have 2 numbers adding up to a number that's in there. So 1, 3, and 4 are all in the same pot now. That's why it exploded. Could we put the 4 over here? Yeah. Could we put the 5 over here? Yeah. Could we put the 6 over here?
No.
No. 2 plus 4 is 6. You could put the 6 here. And then 7. You get gooped either way. So we failed collectively at 7. So that's the $1 million grade 2 problem. And that's from I Say Sure, 1916. Sorry?
Canadian dollars or American dollars?
It's about the same. About the same.
Let's say nowadays.
Just let's say it would be comfortable. After they solve for 2, they go up to 3. What is 2 plus 5?
Whenever students make a mistake, get them to remove all of their pieces and start from scratch.
No. Oh, it exploded!
It does.
2 plus 5 equals 7! Hey, no, not that one. No, we have to start over.
Say it again.
A week after you...
Okay.
Question.
Yes.
I was wondering why it's important that they start from scratch.
It's important that they start from scratch for 2 reasons. The first reason is that kids get confused if you say, okay, well, we can just move that one over here. They start to, it's a harder process than if you just say, start from scratch and put on the 1, put on the 2. The more important reason is story. You want to, it's more dramatic to say, start from scratch, rather than, oh, if you just change a few little things, maybe you'll get the answer. No, it's been a disaster for you, start again. It's much more exciting storyline.
Do you find that if students have discovered patterns in the mathematics that they'll replay, like, because I feel like an advantage of not starting from scratch is that configurations that they found work, they can keep that, but do you find that students will, if they have to start from scratch, they'll go back and be like, no, we know like the 1 and 9 have to be apart because that's the only sum to 8 or something?
Right now, what I tend to do, instead of making the manipulatives, which have their advantages, I tend to just have them write it in their notebook. So they have to start again with a new set of 2 pots. Yeah. For exactly that reason. I like them to build on previous knowledge. But there are advantages also to having the manipulatives.
You have to add 1, so that's 20. Yeah. Divided by, that's 20. 20 is 10.
These students are working on an unsolved problem of mathematics from 1937. The problem is a perfect excuse to get your students enthusiastic about basic multiplication. We set it up through a scene from Greek mythology. King Minos has just imprisoned Daedalus and his son Icarus on a high tower. Daedalus was implicated in the murder by Theseus of the Minotaur, which happened to be King Minos' son. So you can see why King Minos is so angry. Daedalus is an inventor, and so being imprisoned on a high tower gives him opportunity to exercise his brain. And he decides to go about trying to find a way to escape. And he comes upon the idea of gathering bird feathers and beeswax to fashion wings for his son and he to fly off the tower. So that's what this picture is about. On the night before the fateful flight, Icarus has a dream. He writes a number on a rock and he hurls the rock off the tower. If the number on the rock is even, then it's halved. If it's odd, then it's tripled and 1 is added. For example, we could start with 3. Is 3 even or odd? it's odd. So we triple it, that's 9, add 1, that's 10. 10, even or odd? It's even, so we have it. We divide it by 2 to get 5. 5, even or odd? It's odd, so then we triple it, it's 15, plus 1 is 16. 16, even or odd? It's even, so then we have to have it or divide it by 2. Now your students might not know how to divide 16 by 2, and that's okay. They have to take a guess, for example 7, and then they use their multiplication skills to check their guess. Of course it's 8. 8 divided by 2 is 4, because it was even 2. And 4 is also even, so we're going to divide by 2 again to get 2, 1, and Icarus has crashed into the sea. He's dead. This has turned out to be a nightmare of a dream. But Icarus knows that if he can just find a number to write on that rock that doesn't end up at 1, that doesn't end up with him crashing into the sea, that he's going to survive. Daedalus has a similar dream. So in his dream, there's only one difference, and that is that if the number is odd, then it's tripled and 1 is subtracted from the result. So for example, we start off with 3. So is 3 odd or even? It's odd. Triple it, that's 9. Subtract 1, that's 8. 8 is even, divided by 2, 4. 4 is even again, divided by 2, that's 2, and 1. Again, Daedalus is killed. He's crashed into the sea. How sad! But can he find a number to put on that rock so that he doesn't crash into the sea, so that he doesn't end up with 1? So the task of your students is to save the lives of Icarus and Daedalus, to turn these nightmares of dreams into dreams with happy endings. The worksheet has got 2 sides. On one side you help Icarus, on the other side you help Daedalus. Both have a sample that that the students have to do before they can experiment with other numbers. So with Icarus, they have to start with 7, and they have to experiment and see what happens to Icarus if he writes the number 7 on that rock that he hurls off.
Okay, so where's the failure here? What's the other word for failure? The other word for failure is crashed into the sea. He's dead, for Daedalus and for Icarus. Now, one of these, both of the samples are going to end up with him crashing into the sea and dying. So whether you're choosing Icarus or Daedalus, they're both, the sample that I have there, they're both going to die. So I can go up to the students and say, essentially, you failed, right? That you've killed him. You're supposed to make him live, not kill him. So I can have fun with them with that, and then they can choose their own number to write on that rock and to hurl it off and to try to find a solution. Now, one of these is an unsolved problem of mathematics, and the other one, the kids in every grade 4 class that I've ever gone in have solved it. So you need, of course, to balance failure with success, and that's why this is such a beautiful pairing. Okay, so this is a grade 2 problem. Let's see. I'm just going to let you
Let's go 5. I say go 2. 2 is 5.
Last. Looks like the vector droids are attacking Earth again. How do we defeat them? Well, first of all, let's understand how they work. They attack in formations. Here we have 2 ships. They've got 3 circ deflectors each. We can beat them by targeting these circ deflectors one after another. Destroyed. And you can see how it's done. 1 plus 3 is equal to 4 on the back vulture droid. 2 plus 5 is equal to 7 on the front vulture droid. To destroy an entire formation like this, all of those numbers have to be different. Watch out, here's another formation. This one's got 2 vulture droids and what looks like a vector droid. Oh, we can defeat them. We want to defeat these droids as efficiently as possible. That means doing it with as low a number as possible. Now here, our highest number is 20. Can we do better than that? Well, it turns out that we can. And so we must look for that lowest number possible. Here, we found another way to destroy these 2 vulture droids and this vector droid. Here, the highest number that we have is only 13. That's much better than 20. Again, look at how we successfully attacked the vector droid. 7 plus 1 is equal to 8, 1 plus 4 is equal to 5, and 5 plus 8 is equal to 13. That's true for any ship that we're attacking. And for the whole formation, notice that no 2 numbers are the same. That has to be true. Let's see what happens when things go wrong. Here are 2 vector droids in formation. How are we going to attack them? Well, here's one idea. Does this work? No, it doesn't work because there's 2 5s. Again, our attack against these vulture droids is failing miserably. Why? Because we've made a mistake in our attack. Look at this. What's wrong? Well, what's wrong is that 7 plus 5 is not equal to 11. This is your first mission. Destroy all of these vulture drones and try to do it so that your highest number is as small as possible.
So what's the failure here? Failure is, yes, you've destroyed these ships, but sadly it took you so long that Europe's being demolished in the meantime. Too bad. But maybe next time you'll be faster. So that's a success blended with a failure. So this is a grade 8 problem, and here the objective is to wind your way through the labyrinth as the Minotaur, as Theseus in the upper left corner, to get down to the Minotaur in the bottom right corner, in the bottom left corner. And each step that you take must be longer than the step before, and each step that you take must end at a column. So, for example, let's show an example. Here we go. So there's 1, 2, and 3 lengths, and we can add another one. So that took 4 steps total. So that's pretty good, but we can probably do better than that. And so if a child only gets 4 steps and gets to the end, then I said, you've successfully got to the Minotaur, you've killed the Minotaur, but you've been gored in the process. So it's a failure and success mixed together. If they don't end up getting to the Minotaur at all, then they just end up lost in the labyrinth and dying ingloriously. So there's different ways to play with failure, words for failure. This doesn't work because you've got a touch over here, so you cannot have the paths touching, and the consecutive integers must be more. So yeah, there were 2 1s there at the very start, as you can see. So that is not successful.
You can't go straight. Why not just go straight down from the green to the red one?
You're trying to get the most steps possible. If you do that, I will say you reached the Minotaur, you ran up to him, and impaled yourself on his
Okay, so you want many
maximum number of steps. Yeah. So we could try it out and see how many you can do. What you will find is that kids will find a beautiful solution. Let's see. I'll just show you.
Those guys are celebrating because they've just discovered a pattern That is 1, 2, 3, 4, 5, 6, 7, 8 steps. And that was a class record. You can see they're constantly increasing. But they weren't unique. Another group had discovered a different pattern. And this pattern also is constantly increasing. Is this the best Theseus can do? One of these highly regular patterns? Sure enough, these three guys found a pattern that is totally irregular and has 9 steps to it.
And their solution isn't even unique. Here's an... Okay. Go.
So whenever I'm going around, another way to lessen the fear of failure is to, for those that subset of students who do have anxiety, you can lessen that failure by not focusing on them, but by taking it back to the scenario, and to focus only on the scenario, to look at their piece of paper, never look them in the eye, and to say, yeah, it was Theseus who got lost in the labyrinth. It's not you. It was Theseus. Yeah, Theseus got lost. Boy, that must have felt horrible. Or Icarus flew too high. I mean, he must have felt the wax running down his arms. Just to focus on the scenario, another way to decrease the anxiety. Okay. An obvious way to give every student a failure. So we start off with giving the classroom as a whole a failure. To give every student a failure then, one of the obvious ways to do it is to have gradated problems. So that's number one way. I haven't even put it on here because it's so obvious. But for example, this is a Mamitsu problem for grade 6. After the students have solved this, I quietly slip them another piece of paper that might be harder, like this. So I am protecting the slow students, the slow methodical students in some cases. I'm protecting them so that the fast kids don't know that they're the fastest and that this is the loser group and this is the winner group. So it's all done very quickly and quietly so that I'm trying to add a bit of chaos to the classroom to manage, to protect those slow students so that they don't know that they are slow. So I do that with having lots of paper ready and just handing it off quickly to students who start to gloat. Games are a great way to introduce failure, so we can have winning and losing games. This is a grade 6 game.
One of the great unsolved problems of mathematics can be expressed perfectly in the grade 6 classroom as a game. The game takes place between 2 teams. One team starts by saying a composite number, the other team with a prime number. We're going to see how to play this game, and we're going to watch some kids play it.
The red team starts by choosing a composite number. For starters, we're going to make it 12 or under. Let's say 8. The blue team responds by choosing any prime number. Let's say 2. The red team then chooses a prime number, say 7. And the blue team chooses a composite number. Now the blue team is going to win this game if they can make the 2 sides of this equation equal. So what composite number should they choose? They should choose 28. So blue has won. If blue cannot make those 2 sides equal, then red wins.
The game is best explained by playing it in front of the whole class. I like girls versus boys. I set up some seats for the people who choose the composite numbers first, the red players, and some other seats for the people who play the blue first. When most of your students understand how to play the game, let them take out some paper and get at it. One small team against another small team. Remember to keep that initial number, the initial composite number, 12 or less for the first few games. And then you can get rid of that condition, or you could make it 50 or less. did you notice that the girl in the blue started to impose a time limit on the boys? That's very interesting, and please let your students experiment with rules, especially around timing. After your students have played for some time, they should start to get a preference for either the red team or the blue team. Why not bring that out into a classroom discussion? Which is best, the red team or the blue team? You want your students to be able to express why they think a certain team is better. Then go back into the gaming experience. Let them play against each other some more. Let's now look at a typical problem group, kids that aren't fully engaged. One way to get them engaged is to challenge them. And that's what I did with a group that was just not quite there. And so for them, they were trying to really give me numbers that I was going to struggle with. And instead of multiplying out like 44 times 47, instead, of course, I found a prime divisor of 44, and then all I had to multiply 47 by was 4 in order to beat them as the blue team. So now you're going to watch that.
44.
I think 188. I'm not saying that these guys were totally turned around and for the rest of the class sat quietly in their seats and worked on the game, but they at least had a mathematical experience. After playing for some time, your class might end up with the conclusion that the blue team is more likely to win than the red team. And their reasoning might be something like this. They might say, well, no matter what composite number the red team chooses, let's say 13 times 31, blue can always choose a prime factor of it. For example, 13. Red now chooses a prime number, and in order to win, blue has to construct a composite number based on all of the numbers that they haven't yet used from the red side. So in this case, they haven't used the 31 and they haven't used the 2. So they're going to use those, and that will be their composite number. And that will in fact solve the problem. And it looks like blue is going to win this one, and it's going to win everyone. But not so fast. First of all, this is broken down. It's made easy for the blue team. But it's not quite as easy as that if you have the red team say 403 instead of 13 times 31.
This is obviously the RSA conjecture, the RSA cipher. So
if your kids manage to do this, $1 million is peanuts. They'll have access to government secrets, they'll have access to bank account information, they can become master criminals overnight. Whenever I go into grade 6 classrooms and present this problem, I lie. I always lie, and I always tell them that they'll get $1 million if they solve this problem. But there's no reason why this should not be a reality. This is an extremely tough problem. It might not have a solution. So why not get $1 million backing to inspire kids? That's what Mathpickle is doing. In collaboration with the Pacific Institute for the Mathematical Sciences, we are seeking out funding for 13 unsolved problems, one for each grade, kindergarten through grade 12. The prize money to be split between the mathematician who solves the problem and their most inspirational K through 12 teacher. Basis for
I want to leave some room for questioning, so maybe I'll stop here. I'll just summarize the rest of it. So, as well as games, another important way to to give every student a failure is to give them impossible problems. So here I tell them, most of the time I don't tell them that a problem is impossible, but here I tell them that they have to put ballast in this galleon. And the ballast has to be equal on both sides. So they have to take 3 of those 6 numbers from the first group, 3 of those 6 numbers and put them on the right. Add them all up. 3 of those 6 numbers, put them on the left. And if they're equal, then they've managed to win. But only one of those 3 groups of numbers is possible. The other 2 are impossible. So another way to give a failure to every student is to tell them, well, guaranteed you're going to fail on 2 out of these 3 ballast allocation problems. And the last one is, of course, unsolved problems of mathematics that you've been seeing all day, so I'm not going to show you another one. But this is a great way to just have as the backdrop to the whole experience of the class. Yes, you're doing very well now. Yes, you've done another very good job. Yes, 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 yes. But you can see the light at the end of the tunnel is a long way off. Yes?
I just love this. This is the perfect way to end this. This morning, Gwen was talking about low threshold, high ceiling, and what you're giving is low threshold, no ceiling. And what's even cooler, when Glenn was talking about low threshold, high ceiling, I was thinking of the kids in the gym trying to climb the ropes. And I was one of those kids who could never get very high up, and every other kid in the gym could see. And I could see there were other kids way at the top. And I was thinking this morning when Glenn was saying that, how do we give problems where you can't see where the kids are? So that's one thing. Second thing I am totally inspired to do. I actually live in Niskayuna, which is where Ken Rivas, the RSA guy, that's where he went to high school. But 10 minutes away is Central Park in Schenectady, where there is a summer lunch program because the kids don't get lunch in school, with sidewalk chalk and blacktop wall, and you don't have to get the parents to sign up. You don't have to worry about permission or liability. You just recruit some high school math circle to go model making mistakes with colored chalk and prepare them to tell those stories, like no administrative overhead, on a shoestring. This is totally cool. With an iPad, we can bring your videos and the storytelling to like the streets. So this is totally cool.
Please take videos of it, and I mean, that's a dream for me. Sidewalk with chalk is absolutely perfect.
And you really don't have a ceiling out in the park.
Are your videos available?
Everything is free on the website. Even the books, PDF files of the books
so
are
available.
Everything is for free. The keynote presentations, the PowerPoint presentations, and PDF files, all there, along with worksheets, all there for free. Which comes to the awkward point, and that is that I don't know how to make money, so if anyone has got an idea that can help me out, that would be great. So, any other questions?
Solve one of those problems.
Yes.
Do the RSA people know about this? Maybe they would like to give some money. This would be nice publicity, especially if we're doing this in his backyard of his old stomping grounds. I went to your website while you were talking. You have the inspiring pages, and I do feel the need to point out there's only one female pictured in like 30 examples of by heart, who's wonderful, but
she did get #1 slot.
She did get #1. I think you have to find a few more.
Yes, yes. Yeah. Right. Thank you very much.